How's life? Life is past assignment 1, which is good. Anything else? Anything else interesting going on? Everybody's thirsty. Yeah, everybody's thirsty. That's true. We should have brought Coke for everybody in the. Be careful brushing your teeth around here. Okay, so assignment 2 is out. I hope everybody got my message. Assignment 2's deadline got pushed back 2 days because we kind of wanted to start getting on a schedule where the assignments were due in the middle of the week because we thought that would be better. So you'll have a little bit more time on assignment 2. Has anybody taken a look? It's kind of fun. It's kind of fun. Hopefully you guys enjoy it. Okay, so let's do a little bit of review to get started, to get warmed up today. These are the slides we went through at the end of the class, and I wanted to go through them again because I think it makes sense to see them twice. So remember, so last time we were talking about running code on GPUs. And we were talking about, like, what I like to do, I always like to tell or get people to think about, if I have this program, how can I picture how it runs on some parallel processor? So there's all this work, and there's somebody, whether it be a runtime or a compiler or you as the programmer or maybe even hardware, that sort of is looking over here and thinking, okay, here are all the things I have to do. And then kind of looks behind them and says, here are all the resources I have, all the processors, all the cores or whatnot. How can I start assigning things that I need to do onto these processors so that, what is my goal? Really my goal, at least at this part of the course, is just to make sure that every resource I have is always busy. Because if every resource I have is always busy, then I'm probably doing a pretty good job. Unless I created a situation where I introduced a lot more work and so on to do that. Okay, so if you remember from last time, we went through a running example. The details of the running example, it was a convolution, don't matter at all. But what does matter is that every CUDA thread block required a certain number of resources. So first of all, my first review question here is, if I said a CUDA thread, what would you correspond that to in terms of maybe ISPC concepts from assignment 1? Yeah. A what? So a CUDA thread equals ISPC gang, or maybe something else in ISPC. I'd be a little careful about that. And we're talking really completely about both implementation and abstraction today. Yeah. Okay, so why would you say that? Uh-huh. And we have an interesting discussion going on the bulletin board right now about, ISPC gang versus CUDA warp or something like that. But absolutely, I think in your head it should be one CUDA thread is going to map to in its implementation details. When we start thinking about how it's actually implemented, one ISPC program instance basically mapped to a vector lane on a modern CPU. A CUDA thread is going to end up mapping to one vector lane on an NVIDIA GPU, or if you want to use NVIDIA's terminology, one CUDA core on an NVIDIA GPU, and 32 of those CUDA cores happen to share an instruction stream. Okay, so I like that. Okay, so what about a thread block? Is there a concept similar to a thread block in ISPC? Maybe, yeah, because we're going to start distributing these thread blocks onto different cores of the GPU, just like a task. Are there any differences, actually? This is actually really subtle, and I'm not trying to really argue that we should put these definitions in equivalence. I'm just trying to get us to think about similarities. I mean, so a CUDA thread block has this constraint that all of the threads in the thread block are actually all live and running on the processor at the same time. So you can kind of think, like, in some sense, that a CUDA thread block starts to feel a little bit like a gang, an ISPC gang in that sense. But it's just kind of like trying to figure out where you can put these things in correspondence and not put them in correspondence can actually be kind of helpful to your understanding. Okay, so from this example, I defined a program that needed 128 CUDA threads per thread block. And every one of those thread blocks used 512 bytes of shared memory. So I made up this fictitious GPU that every core of that GPU gave you 1.5 kilobytes of shared memory, a little bit less than 3 times the amount that we needed. And every core had execution context for 384 CUDA threads, which would be equivalent to 12 warps. So first of all, what did I mean by why does 384 CUDA threads correspond to 12 warps? And my follow-up review question is, what the heck was a warp? Yeah. Yes? Not you. You means NVIDIA. Yeah. You don't get much of a say in that matter. Or 12 warps, you need to have that many. Right. If you have that many threads, that will get the binary will involve 12 warps. Yes, exactly. Okay. So, and then I proposed, let's start thinking about, so all of our work to do were all of these thread blocks we needed to run. And I think I defined in this problem that we had 1,000 of them that we needed to run. And we had 2 of these cores with some resources. And so how did I start mapping work to do, over here in my analogy, to the resources that I had? I said, OK, first thread block, let's go pick a place to run it on. And I just sort of arbitrarily chose that I was going to put it on core 0, right? So I said, OK, this thread block is now running. This core is executing instructions from these CUDA threads. Everybody's happy. And then I immediately said, oh, well, we have 999 other things to do. Let's go ahead and get the next thread block over here. And there's still more room. So let's go ahead and put another thread block of another 128 CUDA threads over here on this core. So here's a question. We were talking about ISPC tasks as sort of mapping to cores. I'm now putting multiple thread blocks on a core now. And why might I want to do that? What is advantageous about doing that? Can this core run? So given my diagram here, how many warps can a core run at once? In this diagram, not an official NVIDIA GPU, but my cartoon diagram. It can only run 1 warp at a time. And so now there are, in fact, 8 warps active on this machine at once. And why would I potentially want 8 warps active on this machine at once? Yep. Exactly. So multiple warps, multiple execution contexts. That's our latency hiding concept. And if you remember the program last time, if you remember that the first thing that all of the threads in a warp did is they loaded all this data, and then they waited for all the data to come in. Well, while they're waiting, some other warp can be loading data or doing something else, or some other thread block can be doing something else. So we just continued this on, and I actually put a 4th block on this other processor. And at this point, the scheduler that's assigning these thread blocks to these cores had to stop. And why did it have to stop? What was why couldn't I keep saying let's if 8 warps is good, let's go to 12. So why did I stop assigning work to cores at this point? I didn't have the resources up front to guarantee that I could run that thread block. And in this case, the constraining resource was not the number of execution contexts, and in fact was the shared memory. So it should be getting you thinking that the shared memory is not like a cache where if you put too much on the chip, it just thrashes. Like which problem from exercise 1? 1D? 1D, where it was actually better to have 1 thread on the core than 2. Here, this is a situation where the CUDA scheduler is not going to oversubscribe that shared memory. So whenever a thread block completes, like for example thread block 0 in this case, that allows the scheduler to say, somebody's done. Let's give them something else to do. Let's say I'll assign thread block 4. We can go on thread block 5, and so on and so on. Okay. So here's some other review questions I wanted to ask. So imagine this scenario, and you can write a CUDA program that has an operation in it, which is an atomic add. An atomic add says, read the value from memory, increment it by a particular amount, and store the result back in memory as one single operation atomically. And imagine that we have two CUDA thread blocks. A thread in each of these different thread blocks is performing the atomic add to the same address in memory. So in some sense, we can't say that the thread blocks are independent, because they are touching the same data. But the real question is, can CUDA schedule these thread blocks in any order? Because up until now, there's just been work to do. I can take it in any order and schedule it onto my resources, right? The reason why I can schedule work in any order is usually because it's independent. It doesn't matter. It doesn't change correctness if I choose the order. But here's a program where the independence is now starting to get blurred a little bit. Now all of these different all these different thread blocks, these threads and these thread blocks, are reading and writing from the same variables. Can I still schedule this program in any order? Most people are nodding, and I actually would agree. I would agree. So this program, if I tell you that the GPU can write things, it can run your code in any order, run your thread blocks in any order, you could write this code and still feel OK about yourself. Because, for example, if we're just trying to compute the total number of values added into this memory location, the answer is still the same. Because it's associative and commutative in this case. So this is very valid code. But here's another example. Let's say that this is the code in my CUDA program. Is we're going to add 1. We're going to set this value in memory to 1. And then the code in my other thread block is going to say, while not 1, spin. This is a common paradigm that you'll see in pthread code. So this says thread block 1 is going to write a value to some shared variable. Thread block 0 is going to do that. Thread block 1 is at some point in the future going to observe that write and then go do its thing. So now let's imagine running this code on a GPU that has one SM, one core, that for whatever reason can only run one thread block at a time. Maybe this thread block needs 128 CUDA threads, and this GPU only supports 128 CUDA threads. Or maybe it needs enough shared memory that I can only put one core on a time. So what happens if I choose to run thread block 0 first, and when it completes, we'll use the core to run thread block 1? How does the program behave in this scheduling scenario? Yes. Exactly the way we would expect, right? I'm going to run thread block 1, 0. At some point, my flag gets set to 1. Thread block 0 terminates. Its resources are freed. The GPU scheduler puts thread block 1 on the core. Thread block 1 reads that memory address, says, hey, it's 1, and then just goes right through. Okay? But I have license as the CUDA implementer to schedule these thread blocks in any way that I choose, right? So it would also be valid, be compliant with the semantics of the programming language, as if I put thread block 1 on the core first. What happens now? So my claim is that the program will behave differently. Yeah. It will sit here. Thread block 1 will be, I'm just sitting here waiting for thread block 0 to set that value. And because we don't have preemption or anything like that here, is thread block 0 will never run. So this is code that has sort of violated the assumption that thread blocks need to be able to be scheduled in any order. Now, what happens if I have a GPU that could run 2 thread blocks at once? Maybe one core with enough execution context to run through 2 thread blocks, or maybe 2 cores that could run both of these thread blocks at the same time, or interleave them. How's the code run now? Sorry? Well, what do you mean by you don't know? It's certainly undeterministic what order I'll schedule them in, but I promised you that at the very beginning. So what I want to know is, will the program, so the first example, we said the program would behave as intended. The second example, we actually said that the thread block 1 would just infinite loop and thread block 0 would never run. It was a deadlock, or it was a live lock situation in some sense. If I have resources to run concurrently, either simultaneously or interleaved, both of those thread blocks, will I get behavior that I'm satisfied with? Yes, right? So this is interesting that I just wrote a program that its correctness depends on the number of cores of the resources of the hardware. right? So this would be not how I would advise people to write CUDA code. Now, I'll let you take a look at this a little bit offline, but some people, so the real way to think about CUDA is I create all of these thread blocks that can be executed in any order, very much like ISPC tasks, and I'll let this really fancy GPU make sure that it handles the scheduling onto the cores as good as it can. Here's some code where if you look down here, I launched my convolve, and I launched it with exactly the same number of thread blocks that I knew the chip could run at any one time. So I knew something about my GPU, and I said, in this case, it's a GTX 1080, so I can get by with 20 blocks per chip, or 20 chips, 20 SMs, so 20 times 2048 divided by 128, which is the maximum number of threads I can put on an SM. So I know for a fact that all of these can run at the same time. So in some sense, I'm cheating, starting to treat CUDA threads much like P threads at this point, because I know they're all being interleaved on the processor at once. A lot of people write high-performance CUDA code this way, but it's not particularly advisable. So anyways, hopefully those are some examples that you can go offline now and really think through your head, if I create this CUDA program, can I picture in my head what are allowed orderings that the GPU might actually run these things with? Okay, so today, what are we, week 3 into the class? I'm at the end of week 3. We're going to finally start talking about a little bit of how do we make code run faster. And this might be a little bit helpful for assignment 2, but probably some of the later assignments will be actually most helpful for. So everything we're going to talk about today is sort of trying to handle 2 conflicting goals. On one hand, if I have workers, I want my workers to always be working. I'm going to work really hard to make sure that nobody goes idle, just like on day 1 of this class. On the other hand, if I do too much work myself to make sure that people are always working, then I've introduced overhead into this process that may slow down my execution. So I'd like to get by with the simplest possible scheme that ensures that all my workers are always working. That's the tension that we're about to discuss. And this tip is absolutely relevant to assignment 1, because now when we're optimizing code, always do the simplest thing first. Is that the number of students that say, okay, I planned out for 5 days this beautiful algorithm that uses this tree reduction and will scale out to 1,500 processors or something like that, and asymptotically it's ideal, and I ran it on my 2-core CPU, it may not have been the wisest thing to do. And I don't even mean because of time. It means that your asymptotically great algorithm might have overheads in it that mean that the simple algorithm would have run much faster on a 2-core system. So especially in assignment 1, get a correct solution first in the simplest, stupidest way possible, and then start trying to figure out how to be clever. Okay, so let's get started and imagine that I have a processor. Let's go about just to start thinking CPUs again, just keep it simple. Imagine I have 4 processors, or 4 cores in 1 processor, and I have a program that for whatever reason, after I divided it up onto those 4 cores, the first 3 cores, or the first 3 threads, run for this long, and the 4th one runs for this long. So what situation does this remind you of from assignment 1, first of all? In assignment 1, program 1. Because you were asked to diagnose this situation, right? And what caused this problem in assignment 1, program 1? Yeah. So if you did the simple thing that I did, when I gave you the starter code, I said just cut up the screen into equal chunks, and some of those chunks had more work than others. So this corresponds to a situation where maybe 3 of those chunks had the same amount of work, and 1 of those chunks had a lot more work. And it took longer to do, and it slowed the whole program down because for like the last 10% or last 20%, we weren't running in parallel anymore. We were flat out running serially. And that was very much like when I gave a whole bunch of extra numbers for one of you to add up on the first day of class. We were all standing around looking at that guy, I can't remember who it was now, add up a bunch of numbers, and we could have been helping, but we were all idle. So ideally, is if I look at a problem, and so how did you solve the problem on assignment, program one, assignment one program? There were different ways to solve it, but how did you solve it? So how did you solve it? Yeah. So you said that, I looked at the output image, and I expect that if I give every processor every fourth item, that on average, things are going to end up that they're all about the same amount of work. Because the features, so could I have created an image that defeated that strategy? I very well could have, right? But in practice, you're like, well, I kind of know what the workload is. And so this slightly different basic assignment of rows of the image to threads led to, on average, very equal work. And that was very similar to sort of how we talked about the grid solver example, where we said, oh, we could cut it up into big contiguous blocks, or we could cut it up into these interleaved blocks. And you made that decision up front. So we often refer to that type of strategy as a static assignment. And static doesn't need to mean it happens at compile time. It just kind of means, before we saw the workload, we up front said, here's where we're going to how to cut it up. And there was no further synchronization or communication between the threads to figure out who was doing what. It's a static assignment. So here's the question is, when can you get by with static assignment? Because if we could do static assignment, we would love to, because it's like the cheapest possible thing you can do. You don't spend any extra time synchronizing or talking to your friends. You can just sit in your own room and do what you're supposed to do. So what's the major assumption here? Yeah, if we know the workload a priori, if it's predictable. If it's predictable, sometimes we can just take a look at what we know and really exploit that. So the simplest example would be, for example, we know that all the tasks take the same amount of time, and we know how many they are. So let's just put equal number of tasks on every processor. Now, what if I change things to say that the tasks, I know how long they are, but they're all very different? Can I still use a static assignment to properly schedule this onto my parallel computer? So imagine all the bars are of different length, but I tell you up front what the length of those bars are. How would you schedule this program? So my current strategy is I take, there's n things, I take n, I divide it by 4, and I give like chunks of n over 4 to every single processor. That's my current algorithm. And if I know that all of the tasks are the same size, this is a perfectly reasonable way to do things. And now I just change the problem to say, I'll give you a list of numbers, which is the size of all of these tasks. What would be your scheduling strategy now? Yeah. Sorted group. So you would sort them. You would start like sort of filling up one of the processors until it got to total work divided by 4, and then keep going. Yeah, that would be fine. And in principle, that's detailed, but we would just have to cut them into groups where, on average, the groups roughly had the same amount of work. Which, if I told you all the work up front, you could figure that out. And what I'm showing here, showing you the tasks that I've allocated to each of these cores, and then in the light blue, I stack them up, and look, they all kind of come out to be about the same amount of work. So again, all my processors working at the same time. I'm happy. I didn't spend much time at all at runtime in the middle of the computation trying to make sure that nobody was busy or anything like that. And of course, I don't have to take it to the extreme. I could kind of have a hybrid. Like I could sort of take a look. I could divide the work amongst all the processors. And after a while, if I was like, hey, look, like somebody's going idle, I can stop, maybe redivide it again, and so on and so on and so on. So what I'm showing here on this slide is I'm showing 2 example applications from scientific computing. One of them is, imagine you're doing a simulation of stars, and we're going to represent every star by a particle, and that the work we do corresponds to, we need to compute interactions between neighboring galaxies or stars. And so the work that we do is proportional to the density of the black dots. So I could do the things. I could look at the density of the black dots, and I can carve up space to give an equal number of black dots to all the processors. And maybe after simulating the evolution of the universe for a while, the dots would move. And whenever I became unsatisfied with how unequal the work got, I could stop and I could recut up the space again. Another example I'm showing here on the right is this is a simulation of fluid flow over a jet engine. So the white space in the middle is actually the profile of the wing. And you can see that as in the areas by the wing, we have much, much higher resolution to the simulation, because that's where the highest forces are. So they use much higher resolution simulation. And you can imagine if I gave you this grid and I wanted the same number of triangles on every processor, you could divide up that mesh to get about the same numbers of triangles on every processor. And if the mesh changed, we could just redivide it again. Okay. So now let's take the exact opposite approach. In these static assignment approaches, we were like, figure out how to distribute everything up front, and we're going to stay with that policy. We could also say, you know what, let's just make a big list of work to do, and whenever any worker goes idle, we'll have the worker figure out what the next thing on the list is and take the next thing to do. It's like when you go to the counter at the deli and you wanted to buy food, like you take the next item from the queue, and whenever somebody goes empty, like you go up to the butcher, you go up to the guy, and he will service your needs. So what am I doing here in this program? So this is, you should think about this code as C code, but imagine that all 4 of my processors are running this code. So it's running in an SPMD, single program, multiple data form. So what is going on here? This is my sequential program. So it takes as input a list of numbers, and it's going to test primality of all of those numbers. So it's going to take as input a list of integers. It's going to kick as output a set of Booleans. So it's going to compute is prime. And as you probably know, it's kind of hard to predict how long it is. If it wasn't, some things would be very different in the world. So here's my parallel version of the program. So first of all, can someone explain to me how work is assigned to the various processors in my new program? And remember, the code on the right is being run by all 4 processors. So how is work being assigned to my processors? Given that if I would have taken a static scheduling strategy, I would have said loop iteration 0 through n over 4 go to the first processor, and so on and so on. Yeah? So I have 2 questions. So first of all, the explanation was good. So what happens is that every thread grabs the next unprocessed element from the input, does the processing, computes primality, and then it has nothing else to do, so it moves back up to the top of the loop, and then takes the next unprocessed element, which may not be consecutive, right? So what would have to happen for one thread to get non-consecutive elements from the input array? Correct. For example, while thread 1 was computing primality of its current item, other threads may have completed and grabbed the next available item. And so when thread 1 goes back to get the next item, we're farther along. Okay, good. So I would claim here that I created a work queue, and that all of my threads are just grabbing data out of the work queue. But I don't see any code here which says, data type queue. So how did I create a work queue here? Sorry? It's an array of stuff, and I have a pointer to the next available element. So first of all, if you're thinking about how an NVIDIA GPU might execute 1,000 tasks in a single task launch, you can imagine it's almost that simple, right? It's just increment the next pointer and so on and so on. Okay. So you can think about what I just had here as very much a system that looks like this. I have a bunch of work to do. I have a work queue that organizes to do, and I have workers that drain the work queue. And so in the example in the previous slide, what were the round boxes? What did a round box on this slide correspond to? Computing the primality of a single element from the input array. And I said I have 4 workers, and here 4 threads or 4 processors. Good. Okay. So does anybody see a potential problem? This is the same code. A potential problem with this implementation. The implementation is correct. It is not a correctness problem. So does anybody see a performance problem with this implementation? And in the context of this lecture, let me ask 2 questions. Let me ask one question first. Will this result in good workload balance? Yeah? Probably. I mean, if n is like an insanely large amount of things, it's and that testing formality of none of these numbers takes too long. Under those assumptions, I think it will get pretty good workload balance. So what is the performance problem potentially here? Or what do you need to know? Actually, let me ask that question. What would you want to ask me about the characteristics of the workload to know if you actually have a performance problem here? Yeah. So, okay, so you're now wondering, well, you know that this part of the code is sequential, because that's what the mutual exclusion create. So you're kind of wondering, like, I wonder if it's worth it to do this dynamic assignment, because if this takes a lot of time compared to testing primality, we're in trouble. Exactly. Yeah. It's true. Is you could actually get these hot spots. Yeah, you're definitely in a more advanced mode than I'm going to get in this in this lecture. But that's actually also true. Like you could actually try and it is absolutely the case that in some of these systems they randomize the starting times of the various threads to try and avoid that. Yeah. That's an interesting point. Is you could say, what if all the numbers were the value 2? And then the other one was some enormously large 250, huge prime. That could, what problem would that cause? Well, it would finish. It would finish, but most of the work is in a sequential thing. And so most of the program would be sequentialized, right? So let's take a look at this. Let's take at some of the first things we talked about. So let's look at this question of, well, how much time do we spend here in the parallel section versus here in the not-so-parallel section? So in this case, I think I would say that like one task I pull out of this work queue is processing one element. And so, yeah, the workload balance will be pretty good unless we have a situation like you pointed out. But there's a potential for a high cost, meaning that every thread has to take that lock for every single element. And so if I wanted to visualize this on the right, imagine that the blue portions are the point of time. So this is one thread's execution. And the blue portions are time, and time is going down. The blue portions are time when we're actually doing useful work. We're actually testing primality. And let's say that the white portions, let's keep it simple and say the cost of the lock is the same regardless of what's going on, which is not the same as what you were pointing out. That's this white stuff, because it takes some time to actually that lock. And so if this was a sequential program, would I have any white stuff in it at all? So that's overhead needed to manage this dynamic assignment. Okay, and let's just for the sake of argument say it now is a big problem for the code, because all the numbers that I'm giving you are very small integers. Okay, so you are proposing, so first of all the question, well, is it a problem? And you already asked me the appropriate questions for us to determine if it was a problem. If I was giving you only huge numbers, maybe it's not a problem at all. But if it is a problem, your solution is to say, we can probably still get good workload balance if we either increase our task size to multiple elements of the input at once. Or you can think about it as maybe grabbing multiple tasks from the queue at once, right? And I agree with that. So what did I just do here? Can somebody tell me how this code works? What is my solution to reducing the overhead of the synchronization? Yeah. So I decided to take not one, to take a thread, I should say I. Each thread will take responsibility for a block, for a granularity number of elements from the queue at once. And why does that reduce the overhead of executing this dynamic assignment strategy? One-tenth of the time. And here, for those of you who didn't notice, granularity is 10. So I'm taking the lock 10 times fewer, 10 fewer times. Or you can think about it as every time I take the lock, I do 10 times more work. So the ratio of time spent doing good, useful stuff to lock stuff is very different. So there's some tension here, right? So if I choose too large of a task size, things could go wrong, right? Because all of a sudden I might not have good workload balance. Like, for example, what if I said granularity equals n? Right? In the extreme, there's only one task to do. There's no parallelism at all. If I said granularity is 1, we could run into a situation where we spend a lot of extra work managing this assignment. So I'll come back to this slide. So here's a question. What if the amount of time that I spend computing all these prime numbers looks like this? So the height of the bar is the amount of time. And let's say the numbers are ordered in that order. Like this is input sub 0, and this is the last input. Is my dynamic scheduling strategy going to hold up well in this case? So what's not looking good? So for the first part of the computation, I'm in pretty good shape, right? Like I'm well balanced, I'm well balanced, I'm well balanced. And the last part, these last 3 out of these last 4 tasks, those last 3 are going to complete pretty soon. And then before we're completely done, we're waiting for a long period of time for this one processor to complete, right? So does anybody, like, how could you fix this problem? Let's say if you knew that was the input. Let's just say you magically knew that that was the input. Yeah. Right, okay, so here is now I stacked all those bars on top of each other. And this is the problem that you all pointed out correctly, is that one of the cores at the very end got a very long task, and that was this long poll that meant that most of the computation was serialized. And what's being proposed is maybe we should, if we knew this was the case, one thing we could do, if we didn't want to do anything more dramatic, is I could schedule the tasks so that the longest task happened first. So take a look at P4, and now look what's going to happen. Right? So now, even though P4 only does 2 tasks, and all the other processors did far more of these tasks, computed far more numbers, we're pretty happy with this assignment, right? Because we got very good workload imbalance. And it doesn't matter to us that processor 1, 2, and 3 did many more numbers than processor 4. We got workload imbalance, and we got the job done faster. Now, if you saw this situation happening, and you didn't, knowing that the last task was going to be the longest is a pretty artificial. Sometimes like maybe if you're running a job queue, the jobs report how long they expect to run or something like that. What are other things you might try and do if you were in this situation? And don't think about this particular example anymore. Think more abstractly. Like, what are other solution strategies towards to try and, yeah. Okay. So we did the grocery store thing. And so if we had a fast queue, but that even still requires knowing up front. So if we had a fast queue, how would that help us? That basically would, I think I have to get pretty advanced pretty quickly to make that work, right? Because we would get done with all these small tasks, and then we would be pushing all of our big tasks towards the end. So it might actually exacerbate the problem a little bit, I think. I'm thinking through this. But in this case, let's say if I get, well, I mean, in this case, given my pattern, it would probably work out. But I'm actually really worried about having a few people working on the big tasks, because we know we would kind of like to get them going earlier. I didn't actually mean to, like, given the way I've set up the problem right now, I don't think that there's a really clever solution. But one thing that you might be looking at is there any way I can break up this task? Right? Because the real problem is that we have this huge sequential part of our program that unless we can try and find some way to make it parallel, we're going to be in a little trouble unless we know something about the tasks, whether we can reorder them or unless we knew that they were big up front, and so maybe we could give them priority or something like that. So going back to this slide here is, in general, we would love to have as few tasks as possible that we can get by with and still get good workload balance. But in general, we want to make the tasks small so that we can get good workload balance. So and depending on the workload or depending on the cost of synchronization and these things, you'll have to make different decisions. OK, so what's next? Yeah. So here's another question, is by moving to this granularity, what problem was I trying to get around? What problem was I trying to get around? Yeah. Correct, and let's dig into the serial work part of that comment. I knew that this mutual exclusion serialized execution. And really the problem was that I needed to serialize or manage access to a single shared work queue. So if the problem was waiting on that work queue, what does that suggest another way to do better might be? How can we alleviate the contention, right? And in fact, we never actually came back and talked about the one barrier problem that some of you thought about. But that was kind of the same problem, right? Remember, we had all those barriers because we had one global diff value that we had to kind of protect. And the solution that some of you came up with was to actually replicate the diff value and use different diffs and different dones and different iterations. Same thing's going on here. We have one queue, which means everybody has to synchronize on it. And so one could imagine a situation where maybe there were a bunch of different queues with work. Maybe every processor had a work queue for itself, and that it normally only accessed its own queue, but only when it ran out, it might go and try and find other work in some other processor's work queue. I'm about to talk in a little bit more detail about an algorithm for managing this. The last thing that I want to point out in this section of the lecture, though, was that if we have a work queue, it's not necessarily true that all the tasks can be run in any order. So we could specify dependencies between those tasks, and the system that's distributing work to the cores would need to respect those dependencies. So this is exactly at an instruction level what an out-of-order instruction scheduler actually does. But you can imagine that a task scheduler does it as well. OK. So does anyone want to talk about this multi-work queue solution? Can you talk about that before we move on? Yeah. OK, so first of all, I love your intuition. Why are we talking about something complex when I feel like the simple solution is going to be fine? So why are you saying that the simple solution is it's fine? Yeah. We solved it by the multiple granularity thing. Done.
Well, the problem with the granularity was like striking the balance, workload imbalance, and serialization.
Yep.
I'm wondering, it feels
your intuition is completely sound. I'm not going to answer the question because I'm going to answer it over the next 25 slides. But but I like everything you're saying makes total sense to me. Yeah. He has a response. So the question was, it seems like making the problem more complex or having multiple queues will either just make it harder to ensure good workload imbalance, or maybe introduce additional synchronization overhead and whatnot. So you're like, how can we even make it any better? And he retorts, I think that's a good intuition as well, is that, if we're only dealing with 4 processors, taking an atomic integer read, modify, write is not that bad on a modern multi-core processor, right? But if we're talking about programming a supercomputer that has 100,000 processors, or we're talking about just a bigger machine, maybe over a cluster or something like that, then the calculus of what the overhead is compared to the work is could change very dramatically. So you're absolutely correct in saying we should not deal with more sophisticated techniques until we have to. But maybe at some point we'll have to. And let's go talk about how we might address it in the situation where the contention is too much. OK. So far in this class, we've really talked about very simple parallel programs. And most of those parallel programs could basically be described as data parallel programs. I had an array of numbers. I performed the same operation on all of those numbers. And we've talked about several ways to express that pattern. Like, for example, in ISPC, we had ISPC for each. In ISPC, if we were data parallel over coarser granularity, we could launch tasks, like take this ISPC function, launch it 1,000,000 times. Last time, I told you we could launch the CUDA kernel foo on thousands of threads or thousands of thread blocks. In 2.10, you would have mapped a function onto a sequence. And we haven't talked about OpenMP, but some of you might have written C code, and I can add to a for loop in C some extra compile directives in modern compilers to say, hey, trust me, these loop iterations are independent. Go ahead and try and run them in parallel. And we haven't talked about that syntax. And so that was one way of thinking about code. Another way of thinking about code is just in terms of good old p-threads. We're not going to think about a function that we map onto this array of elements. We're going to think about launching 2 p-threads, and then we're going to write some code that tells what those p-threads should do. That's your standard p-thread programming model. But there's another class of algorithms that really lend themselves to sort of thinking very naturally about parallelism. And for those of you who've taken 2.10, this should be very, very natural for you. So I put quicksort up on the board here. So just to make sure, how many people have seen quicksort? So I wasn't going to spend any time. So everybody's seen quicksort. Just a quick refresher, we have an input array of elements that we want to sort between begin and end. We are going to partition the elements to the left or to the right of some pivot. And then we will recursively sort all the elements to the left of the pivot, which are less than the pivot value, and recursively sort all the elements to the right of the pivot, which are greater than the pivot value. So are the 2 calls to quicksort after I've partitioned the items, are they independent? Yes, they are. So in many of the applications we've seen so far, the parallelism was huge. I can parallelize all 1,000,000 iterations of this loop. So all the parallelism was just present at the very beginning. Now the parallelism, well, it's only 2-way parallelism. So can I run this code? Could I be able to do very well on a processor that had 4 cores? Because I only see 2 parallel things here. Yeah? So keep in mind that it's recursive. So even though we might be sequential at the very top, we then very quickly get 2 parallel things to do. Then we have 4 parallel things to do, and so on and so on. So you could imagine that rather quickly we would be able to saturate the whole machine. So the parallelism in a program like this sort of reveals itself slowly and reveals itself very dynamically as well. Is that as we're running the code, more and more parallel things to do start to pop up. So these divide and conquer algorithms are always very parallel, but they create these situations where the amount of parallelism is large down here, but not so much at the very beginning of the program. I'm going to tell you about, so how many people here have actually seen the Cilk programming language? You might have seen this, only one, really. I thought we did Cilk at the end of 210 now. Yeah, okay, so again, how many people have seen the Cilk programming language? Okay, raise it a little bit higher because I'm actually curious. So only like 10 people in this class remember the last assignment in 210?
They changed it.
Oh, they changed it, really? Oh, okay. Wait, is it, so it's not, it wasn't? What was it, what's it now? How do you create parallelism? Okay. Well, for those of you who haven't seen Cilk, it's worth seeing, because I only need to tell you two things. Cilk gives us the opportunity. It has one construct for calling a function that creates parallelism, or creates independent work, I should say. I shouldn't say parallelism. I should say independent work. And another construct for waiting until all the independent work you've created is done. So normally in C++ or C, if we call a function, control transfers into the function. When the function returns, control returns back to the caller. In Cilk, I can Cilk spawn in front of a function, and the semantics of that call have now changed. It says, this function can now be executed independently of the caller, and potentially asynchronously and in parallel if you so wish. Cilk sync says, everything that I have spawned must have finished before I continue on past that statement. So let me give you two examples to help you make a little bit more sense. So first of all, if you want to think about Cilk spawn as a pthread create, that could be an implementation of it. And if you wanted to think of Cilk sync as a pthread join, that could be an implementation of it. So let me give you some code examples. So first of all, let's look at the first example. And on the right, I'm drawing you the dependencies between the logical threads of control that emerge in the program. So the first program says Cilk spawn foo, then run bar in the calling thread, and then Cilk sync, which means the calling thread will wait for its previously spawned foo to complete. So notice how the dependency graph, every edge, so up there is the calling thread is straight down in time. It spawns off foo, runs bar, and then syncs on foo. So that dependency graph, does it say that foo and bar have to be run serially? Or does it allow foo and bar, if you had parallel execution capabilities, to be run in parallel? Who thinks foo and bar can be run in parallel? That's correct. So do they have to be run in parallel? Time could do something and say, you know what? Screw you. I'm just going to treat that Cilk spawn foo as a normal function call, and the program is still a correct program. Okay, so let's look at the second one. Cilk spawn foo, Cilk spawn bar, Cilk sync. So actually, who thinks there's the same amount of parallelism in this code as the one above? It's actually the same amount of parallelism. So foo and bar were spawned off, so they're independent. But the calling thread doesn't have anything else to do. It just sits there and waits. So you get a slightly different dependency graph, but from a meaningful work perspective, we still created two pieces of work. The first program is modestly better than the second because there's just lower overhead to spawn off two different things. Or sorry, to spawn off one thing. And then just a slightly more complex example. Let's spawn foo bar fizz. Let's do buzz ourselves, and then make sure that foo bar fizz is done. And so does this graph should make sense to everybody here. So what are my options if I have a two-core processor given the code has now running the Cilk program has exposed this parallelism to Cilk or to this runtime? If we run this on a two-core processor, there's a bunch of different valid orderings, right? I could run them all sequentially, correct. I could run buzz and fizz on one core, bar and foo on another. There are many, many options. So notice here that Cilk is just really is like epsilon away from your sequential code, but it just allows you to really, really conveniently express a little bit of parallelism, a little bit of divide and conquer parallelism when you want. So notice that Cilk spawn does not say execute this in parallel. It says that You may execute this in parallel when you like. Cilk sync is very much a constraint. Sync tells me about order. Everything that was spawned on this thread before the sync needs to be completed before the sync returns to the caller. Yes? No, and again, I want to be very, 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 let's first bullet. Notice that Cilk spawn abstraction does not specify how or when spawn calls are executed. So if I told you that Cilk spawn means create a pthread, I'm very much ascribing more to those semantics. The only thing Cilk spawn means is this function call can be executed in a different thread in parallel with the caller if someone so chooses. And really, someone means the Cilk implementation. And now I'm about to talk to you about how the implementation works. Okay? But I would like to go to a slightly more complicated example, or go back to our quick select example. Given that you've now seen these dependency diagrams, how might this work for quicksort? Excuse me. I'm not showing you, I'm not wrapping the outermost call to quicksort because I ran out of room. So the first partition is the partition called at top level. And then notice that we spawn one subcall to quicksort, and we do the other quicksort call on the calling thread. We could have spawned two calls to quicksort, and it would have been essentially the equivalent. But that would be like using the second form of programming style. And I told you that the first form is a slightly more proper Cilk programming style, because we should only expose the necessary information. And then, of course, those quicksorts end up spawning two more quicksorts, or break into another spawn of quicksort, and so on and so on and so on. And at some point, there's something interesting in this program, right? What's this if statement doing? If something is less than some parallel cutoff, what's this if statement doing? It says that, you know what, we should not be recursing all the way into one element. And why do you think that maybe we should insert that into the program here? Yes? Might not be worth the overhead of whatever bookkeeping that I'm about to tell you has to happen to potentially move that job over to another core or something like that, right? And in fact, Umut's system built on top of C++, one of the things that he was trying to do, I don't know what this, but one of the research papers that Umut wrote recently is trying to take a look at these programs and automatically insert that termination condition for you. It is kind of like one thing that's kind of interesting is that I'm telling you don't think about parallelism at all. It's just declare independent work. So I kind of just told you don't think about scheduling. Just write your recursive function the way you want. But now I've said, you know, there's one part of scheduling you need to think of, which is it's up to you to set the granularity of the work. And so the system that Mood is having you guys work in 2.10 is trying to handle additional parts of the scheduling for you that Cilk does not. Right, and that's exactly what you said. It's like sometimes just doing the sequential algorithm on one core is worth not synchronizing. Okay, so the main idea when you're writing a Cilk program is you kind of have two responsibilities. It's expose as much parallelism as you can, let the scheduler sort it out, but just make sure that your granularity of the minimal possible amount of parallelism is large enough that the overheads that the scheduler are going to incur don't swamp your performance. And a nice rule of thumb is you want big things, make them as big as you can, but make sure that you have enough work that's about an order of magnitude larger than the size of the number of cores that you have. All of us try to say, yeah, you know, if you have 100 cores and you don't have at least 1,000 things to do, there very much could be some raggedness at the end. Okay, so let's start talking about scheduling these programs, right? And the question in your mind is, how can we do better than just calling pthread create for every spawn and pthread join for every sync? Okay, so first of all, I'm going to take the same tried and true scheduling strategy that every system we've dealt with so far has. I am not going to call pthread create for every single spawn. I'm going to set myself up with a pool of worker threads. If I have 8 cores or 8 execution contexts, I'm going to fire up 8 threads, And the name of the game is to take those dependency graphs on the right side of the screen and map the nodes in those dependency graphs onto my 8 threads. That is the job of Cilk. You can think about these threads being booted up when the program launches. In general, almost any runtime says the first time you spawn something, that's the time at which the threads actually get created. OK, so let's consider a much simpler problem right now than quick select. So let's consider Cilk spawn foo bar Cilk sync. OK. So I need to give you a little bit of terminology, is that very much echoing the diagram, I'm going to call the branch, the leaf off the trunk, or the function that is called, I'm going to call that the child, because it is a child of the current thread of control. And then I'm going to call everything else on the current thread of control the continuation. So if I have one core, and there was no Cilk spawn there, this was normal C code, would we run the child or the continuation first? Sorry? The child, right? Because C would just would enter the function call would return, and then we proceed with the continuation, so to speak, the rest of the thread. And Cilk is designed so that if you actually just remove the Cilk spawn and Cilk sync keywords from a program, you get a valid single-threaded program that does essentially the same thing. OK. So now the problem, but now it's not sequential anymore. Now let's say you have a pool of 2 threads. Now you have a choice to make. So what happens if we do the same thing that normal C semantics do? Thread 0 calls spawn. Thread 0 runs foo. Foo returns. Thread 0 runs the continuation. Who's happy with our performance on that? Not so good, right? OK, so now you have OK, so how might you schedule things a little bit differently? And I jumped ahead. That's the single-threaded version. And what we said is that we're assuming that thread 1, while thread 0 is executing foo, thread 1's not doing anything, right? This is a complete waste of resources. OK, so help me improve my scheduler. Help me improve my scheduler. Yep. OK, so you said that what we're going to do, we're going to ship our child off. Thread 1 is going to work on the child. Thread 0 can continue on with what it was supposed to do. Is it running? I forgot the program. Is it bar? It's running bar, right? Yeah, it's running bar. So thread 1 runs bar. Thread 0 runs bar. But I could probably do it the other way, right? I could have thread 1 run foo, thread 0 run foo, and I could have thread 1 start running bar. Exactly, right? So I have to set it up. It's sort of, it's an interesting look on what we should be doing here. OK, so let's start thinking about the implementation details. So now I want you to think about every single one of these threads as having a work queue. And that work queue is stuff that thread needs to do next. So when we get to any Cilk spawn, you can think about the Cilk spawn as potentially putting child or the continuation onto various work queues. So in this example, what I've said is, OK, thread 0 is going to start by immediately running just like a C program. It's going to run the child. It's going to run foo. And in fact, it is executing foo. But foo can run independently from the continuation, from bar. So we're going to put bar on the work queue because this thread, it plans to do bar next. Make sense? But bar says, but now that it's in the work queue, we're saying that, well, this is something that can be done in parallel with what I am currently doing. And I just want to let everybody know, in my work queue, I'm going to do it next. And now when thread 1 goes idle, thread 1 could go over here and grab the latest item out of thread 0's work queue. It can steal the work that thread 0 planned to do next. And if thread 1 steals that work, then we situation where, well, it just kind of puts that work in its own work queue and then just starts processing its own work queue again. And now we're in a situation where both foo and bar are running in parallel on the two processors. Yes? Because thread 0 would prefer to only manipulate its local queue. Contend for a shared queue, because we said that was terrible. Right? So, and 0 planned to do bar next. You might as well put it right on your desk. It didn't know thread 0 was out of work, and it didn't check in with, it didn't know that thread 1 was out of work, and it didn't want to check in with thread 1 to figure out if it was out of work, because if one was busy, we might as well not bothered it and just gone on with our day. Okay, so this presents an interesting question. I just gave you an example when we were on something, we put the continuation on the work queue for stealing. You gave me a situation where you wanted to put the child on the work queue for stealing. And those are two valid implementation options here. So, which one do we choose? And I probably am not going to give you a satisfactory answer to which one is best, given this simple example. But I do want to I can highlight a program that does make it very clear that the choice that we make leads to some very different trade-offs. So imagine this for loop. For I equals 1 to n, which is a sequential for loop, the body is, well, for each loop, we're going to spawn off parallel work, or potentially parallel work. So notice that this is what the dependency graph looks like, right? I have one thread of control, and I have all of these potentially parallel loop bodies that are all children forking off of it. So if I run continuation first, what I'm doing is I'm putting the children in the work queue. And what I'm going to do is that the continuation thread is going to immediately fill up the work queue with all this parallel work to go do. You see why by running the continuation first, why the work queue will end up with 10 things in it. You see that? Okay. So if no stealing occurs, the order in which this thread will run its work is very different than the serial program. In fact, it's backwards in this case, assuming that we pop the last item off the queue. Assuming we treat it as a stack and not a queue. Okay. So you can think about this as almost like a first traversal of the call graph. So I could actually blow up and have O of n space. Now let's think about the opposite. We're going to run the child first. We're going to behave much like a C program. If we run the child first, we're going to put the continuation on the work queue, and the continuation was the original thread at the top of the second iteration of the loop. So we're working here on foo 0. The next thing we'll do is the next iteration of the loop. And so if I just run this with no other thread involved, it will run in exactly the same jump into the callee, back to the caller order as the sequential program. And if thread 1 here, sorry. If thread 1 wants to steal the continuation, it just gets grabbed up, and thread 1 starts by executing iteration 1 of the loop now. And it spawns another, we get the next slide. It'll spawn another piece of work, and so on, and so on, and so on. And so the thing is just going to be bouncing back and forth between all of the processors. But, and you can actually prove that the total amount of space that you need, like the total number of jobs in the system, actually never exceeds the sequential program by more than a factor of t, where t is the number of threads of the processors. So it's a lot more space efficient. Okay, so now let's ratchet this up to a real example. So let's go back to our scheduling quicksort. So notice that I didn't really decide that anything was best at this point. So quicksort's doing its thing, and let's see if you can convince yourself why this is correct. So quicksort has spawned the first half, recursed, and so on and so on. So for now, I'm putting the child into the queue. I'm running the continuation, right? Is that the first thing I put in the queue was, I'm running the child, which means I'm putting the continuation in the queue. The second half went in the queue, and the second half of that half went in the queue, and the second half of that half went in the queue. So can you think through, can you confirm that this is the state of the queue after 3 recursive calls? Assuming that we run the child first. Make sense? So we put 100 to 200 on the queue. That's the continuation. The child is 0 to 100. Then we put 50 to 100 on the queue. The child is 0 to 25. Put 25 to 50 on the queue, and so on and so on. Okay. So thread 0 is working on some subcall to quicksort. It's established that these subproblems can be done in parallel. And all my other threads, all my other cores are sitting there idle. So it makes sense that it is time for these other threads to go grab themselves some work to help out. Because thread 0 is over here going, hey guys, this is ridiculous. I'm doing all the work. I've got this huge pile of things I need to do later. None of you are doing anything. Can you help me out? So here's my question for you. Thread 1 wants to steal some work. It has 3 options. Do you feel passionately about which one it should steal? Or do you think it does not matter? So think about this just a little bit. Yeah. So you're saying that you would like to steal 101 to 200. Okay, why would you like to steal 101 to 200? You are greedy. You are stealing the largest thing to steal. Uh-huh. You have to steal again. I like that last part of it the most. Is the thing I want to stress here is it kind of makes sense that if you could steal something, a really short thing to do, or you could steal a big thing to do, let's go steal the big thing to do because hopefully I won't have to steal again for a very long time. And you can imagine that stealing has got some overhead in it. I have to go over here. I have to manipulate some data structures. I have to pull the data back. I might even have to take the execution context and pull it over here. So it does make sense to steal from, if this is the bottom of the queue, to steal from the top. And that's exactly what I did here. Yes? I am, because I'm about to use the term deck. Did I already go to the side? I was about to say that really that queue is not a work queue. Now I want you to start thinking about it as a proper deck data structure, right? And that the local thread will be manipulating, inserting, and removing work from the bottom of the deck, which is the smallest stuff. And at the top of the deck is the biggest stuff. And so when another thread wants to steal, it will steal from the top of the deck, which actually has 2 really nice properties. First of all, you steal the largest amount of work, so you don't have to synchronize again for a while. And secondly, when we get around later in the course to contention, it means that this thread and all the other threads are operating on different sides of the data structure and can avoid contending for the same locks and things like that. And in fact, you can actually implement a deck like this in a completely lock-free way, so these can be very, very fast. Yes? It's a great question. So it turns out, and I'm not going to talk about it in this lecture, but it has been proven that basically the right thing to do if you know nothing about your workload is to randomly pick another person to steal and not actually steal from the person that has the most work or anything like that. So if when a thread goes idle, they randomly pick a queue and victimize a deck and victimize that deck, you can prove theoretical optimal bounds. And in fact, this work was done at MIT. Okay, so got it. So now that we've stolen, now we can just kind of run in parallel, right? So now there doesn't need to be any communication at all between the threads for a while. These threads are all just going to run. They'll start generating, they'll start generating more work, and they'll just fill up the machine. And so threads are just pushing onto their local deck, popping from their local deck, no inter-thread communication, and until someone goes idle, there's no need for any shared queue or any communication between the particular work lists. And you guys jumped ahead of me, is that the theory actually says that if you go idle, you should steal from a random thread, from a random deck. Okay. So now let's go back to that question I asked you about should we run the child first or should we run the continuation? And it turns out the run child first scheduler works pretty well. So let's go back to this loop here and notice that in the original example when we ran the continuation, when we packaged up the child for stealing, one single thread was responsible for generating all of the parallel work. So we actually serialized the process of exposing to everybody else the work, in addition to having to keep a record around for every iteration of the loop. So imagine this was 1 million iterations of the loop. So Cilk actually has one other construct in addition to spawn and sync. The other major construct in Cilk is actually Cilk for loop, Cilk for. And Cilk for, it would just, you just write it Cilk for, would actually be implemented like this, as divide and conquer recursion. And why would you think that this might be a very efficient way to, or a much more efficient way to expose parallelism than this here, if it was run in a run child first scenario? Yeah. Right, so what happens is, rather than like trying to generate a bunch of work for everybody to steal, we just divide the problem in half. So someone else comes along and steals the entire other half of the problem. And then together, we now generate a bunch of work. So now I have two threads generating a bunch of work, and so on and so on. 4 threads or 8 threads. And as soon as I get to the same number of parallel things to do that I have cores in the machine, all the threads just stop communicating because there's no need to expose any more work because everybody's busy. So this thing is just going to do divide and conquer down to your 8 cores. And then those 8 cores are just going to start running sequentially. They're never going to communicate it again until the workload imbalance problem rears its head. Whereas here, we're going to generate 1 million little foos, and everybody's going to go off and try and continuing to steal somebody else's foos, and there's a lot more synchronization overhead and a lot more space. Yeah. So it's saying if you have a system that runs really well for divide and conquer, your for loop better be implemented like that, otherwise you're in trouble. Now, if all you were doing was writing a data parallel program, there are much simpler ways to partition the data parallel program, which I showed you at the beginning of this class. Exactly. OK, so I'm going to stop here, because the only other detail I haven't told you is the details of how you manage the sync. Because now there are threads all over the machine running parts of this code that I, as one thread, need to understand, are they all done or are they all not done? How do we actually bookkeep that? But so that's Cilk. Cilk is, if you're doing any kind of algorithms, parallel algorithms research, or definitely if you're running divide and conquer algorithms, Cilk is a very elegant way to express those problems.